Good afternoon. So today I want to continue our discussion on recursion. I would like to go over some examples to just drive the point home as to how you've already seen recursion before, give a couple examples of how to utilize it now, and then I want to connect it with your next homework assignment, which is about saying, okay, how do we use the tools that we've created from before, like the file classes, to sort of take new things that we've learned, use them with the old things that we've developed in a way that makes coding really nice and enjoyable, okay, for very high-level thinking activities. So before we get to that, let me start with the code that we developed for the file system, okay, reading from file, writing to file. So I posted that on CCLE in the form of a text file. And really what I want to do is I'd rather put this into header files and CPP files. So let me do that right now, just to kind of emphasize, you know, we started writing these classes for fraction. We had, you know, a bunch of function declarations up top, and we had a bunch of function definitions below main, and we put it in a header file for the code from the class, and then we made a .cpp file which contained a bunch of extra, or just all of the functions. And remember, for all of your functions, you have to, in the definition, you have to write appropriate comments. Okay, so usually I do it, but sometimes I do a little shorthand notation, which is just ... Okay, but yes, this \** indicates to this program called Deoxygen, for example, that this is a special kind of comment, and that this is actually something that it needs to pay attention to when it writes documentation. Okay, so let me just show you guys why we do this. If we look at the fraction class, here is @class fraction @brief stores int over int. Here is points.h. You'll notice point2d has a comments, and color point2d does as well. Let's just, okay, so let's run this Deoxygen program. And I think I've already prepped it for this. Yeah, okay, so I've already prepared it for this, for these files, okay? So when I run, okay, it's going to go through all my files and check for all of the specific commenting styles. And then I click Show HTML Output, and now I've got a fairly well-organized set of documentation. This is an HTML file. You could literally put this on the web. Okay? It's clickable. It's all linked up. If I look at classes, there's my point2d, and there's my comments for it as well. So it says stores XY coordinates as double. We look at the comments say stores XY coordinates as double. I have an example there. If I click on point2d, it tells me my the example that I created. That's the code that I wrote. Looks like I need /n. So let me show you just how easy this is to modify. I think I need a /n here, and a /n, and a /n. So then we just rerun it. I'm going to close out. Well, I'll keep it open. Show HTML. We go to classes. We click on point2d. We go to more. And there it is. There's my example created right there. Okay? So it automatically created all this documentation. Here are the member functions, point2d, the default constructor, the constructor with parameters. There's a move, a print, a virtual destructor. It even includes a inheritance diagram. Okay? So we say, oh, okay, color point2d inherits from point2d, and we can click on that, and it takes us to the color point2d class. Okay? Takes a point2d and adds a color. Okay? If we go down here, these are functions that I haven't documented. So if I take a look at, say, this move function for color point2d, if I go to my points, okay, there's my move function. Notice I didn't put any comments in. If I put in comments now saying, you know, moves the point by coordinates, say x0, y0. At param, move by x is x0, or the x shift. At param, move by y is y0, or the y shift. Doesn't return anything, so there's not any at returns anywhere. Now, if I run deoxygen again, classes, color point 2D. If I go to move, there's my documentation. Okay, moves the point by coordinates x0, y0, parameters. Okay, so this is very important if you are writing hundreds and hundreds of thousands of lines of code, because you will write code which 6 months from now you won't even remember what it does or why you did it the way you did it. Or you might look at it and say, oh, I was stupid back then. I know a better way of doing it now. And then you rewrite it and you mess it up. Okay, so these commenting styles are very important. Another thing, though, is that no, let's just leave it at that. Okay, so like I said, the commenting is very important. I should have another one up here. And remember, \* at file, not fail, file points.h at brief stores the points point 2D, color point 2D, etc. Classes. Give a short description, or maybe a more detailed description of, point 2D class is the base class for a bunch of other classes. Okay, now if I look at currently the documentation, if I look at all my files, I have documentation for fraction.h and fraction.cpp. Now when I redo it after having put in those comments in points.h, now it updates it there. Now where's my points.cpp? So here, wait, oops, points.cpp. That's what I meant. Okay, there we go. You can fool it too. Let's do it again. Go, click on files. There's my points.cpp, and then it shows up the points.h file without any documentation on it. Okay, so if I go to points.h, probably nothing in this file is well commented. Yeah, there's no comments at the top here. So I can put it up here. I can say at file, points.h, at brief, header file. OK, I think you get the point. So let's take the code from, oh, my mouse is going phantom on me. OK, there we go. Let's take the code for file reading and writing, and let's put it into its own file, which we're going to call, I guess, what should we call it? Maybe we'll call it file system, something like that. Okay. So now it's going to automatically try and create a class by this name, but the only reason I went to create a class is because I wanted it to automatically generate the .h and .cpp files for me. I'm going to delete those just like I did with the point2D or the points class. So I do file system. I get rid of this junk here. I go to file system.cpp. I get rid of this, and I'm going to replace it with, excuse me, precisely the code from last time, which is, okay, well, let's take the we'll get rid of some of these classes. Okay, so we'll take all of the declarations, copy, and we'll put them in here. Okay, and we should definitely add comments to these classes at some point. But let's get rid of those later. Okay, then we go to file system.cpp, and we take all of this code here, and we put it in like so. Okay. Now we go back to main. And this is pretty much just code I copied and pasted from another text file anyway. So are we going to use this today? Well, maybe. OK. So now if we number include file system.h, square data, multiply defined symbols. This happens a lot, actually. OK, so let's see. Square data. I think we just have to write inline. Yeah, OK. What happens is I declared and defined the function in the header file, which I can do as long as I declare that this function is inline. In other words, the declaration is going to also contain the definition. OK? So I could either write inline, or I can declare, copy and paste into the .cpp file the definition. So here I just wrote inline. And now I have access to my read from file and my write to file, or output to file. What did I call it in the homework? I think I called it write to file or something, right? Yeah. Let's not change it right this moment. OK. So actually, let us change it right this moment. OK, so write to file, and we're just going to copy and paste. There's only a few of these, okay? Just to kind of show you how relatively straightforward it is. And yes, this is what you would literally do. So some programs like Sublime will let you edit all instance of a particular variable or word or set of characters all at once. So you can say find all instances of output to file, and replace it with write to file, and very quickly it just replaces all of them with one command. So there are a lot of great tools out there to help enhance your programming, and Visual Studio is one of them. OK, so now we can do things like, I don't know, write to file. Let's call it my file. Output. Oh, let's try outputting all the permutations. OK, let's see. So if I can see out it, let's see. How would I do this? File system, what did I overload it? I overloaded an int and a string. Let's print a vector. Of ints. OK? How we're going to do that is we're going to just do a for loop, just like in the code here. So, we want a vector, I guess a vector of strings. OK. Vector of strings. OK. So let's call it oh, no, we just want to be able to output strings. This should work right away. OK, I was misreading the code. Forget about vectors for a moment. Let's just replace cout with output. And I am going to have to get rid of endl. I do apologize for this, but I'll tell you at the end, towards the end of the quarter, you'll see why I have to replace this with /n. OK, look at that. It compiled. All I did was swap out cout with the write to file. OK? Now let's run it. Press any key to continue. Now let's check out. My file. And there we go. Okay? So it's as simple as that. Once you have all the infrastructure in place, then you can do this file reading and writing as if it was the console, and now you have it saved somewhere. You can copy and paste. You can search for, say, the pattern A, B, D, E. Cannot find it. A, B, C. Found it. Found a bunch of stuff. OK, so this is the advantage you have when you utilize the existing infrastructure, and the amount of code you need to write in order to do it is pretty minimal. OK? So that's that example there. now we can rerun the deoxygen and regenerate a new source of documentation, but we should really go back at some point and just fully fill in all of those comments. And for your homework, you do need to do that. Okay, does there any questions on what I did just there with the file, and I put it into the header in CPP, and then I started using it right off the bat? Okay, so let's continue with how to think recursively. And we're just going to go through a couple of examples and set up a framework for how you should break down the solution to a problem into smaller components and how to recombine them. Okay? Ignore that slide. Okay, so let's just recall two very famous functions, which you probably are aware of, but even if you're not, it doesn't really matter. All that matters is the formula that I've written on front right here for you. Okay? You just have to be able to understand what the formula is telling you. So there's the factorial function, and this is the one where the factorial of, say, 10 is just the product of all the smaller integers. Okay? Very simple. Now, you probably thought of it more like a for loop, right? You probably thought of it like, oh, if I was going to compute the factorial of 10, I would probably do a for loop and do 10 times 9 times 8, do like for I equals 2, I less than or equal to n, I plus plus, and then times equals. Okay? But there's also a recursive structure here, which is, well, take out a factor of n, and you multiply by the same function with a strictly smaller input. It's a recursive function. Also, 0 factorial is 1. There are many good reasons for that. You just kind of accept it. 0 factorial is 1. Fibonacci numbers. This is related to, I think, rabbits or something. You guys have probably seen these in some form or another, but basically it's a sequence which adds the two previous numbers in the sequence, and it just starts out with some initial conditions. The initial conditions are actually somewhat arbitrary. You can put whatever you want there, and there are generalizations to the sequence that put in like an A here and a B here, and like for A 5 and B is 7 or something, like what is the sequence? Are the properties of the sequence any different? Okay? So here we just choose f of 0 is 0, f of 1 is 1, and then f of 2 is going to be 0 plus 1 is 1, f of 3 is going to be 1 plus 1 is 2, et cetera, et cetera. Okay? It's the usual Fibonacci's that you may have seen before. But in particular, this is a recursive function that relies not just on calling the previous or the function on just one smaller input, but on two smaller inputs. Hence why we have two initial conditions. Okay? So now we take a tip from your book on a 4-step procedure for thinking recursively. 1, you think about various ways for simplifying inputs. In other words, how do you get the exact same function with a smaller input? How would you combine what you took out to get that smaller solution, or the smaller problem, with the simpler inputs to a solution of the original problem? In other words, I took something out in order to call the function on smaller inputs. How would I recombine it, assuming that problem was solved? Step 3, those are the main meats of the matter. The main meat of the matter, those two steps. But then step 3 is, okay, well, if I have to solve a problem of a smaller input, I have to stop the chain reaction at some point. So I need to specify what happens in these base cases. They're called base cases. Okay? So find solutions to the simplest inputs. That's like your f of 0 is 0, f of 1 is 1. And then step 4 is implement the solution by combining the simple cases and the reduction step. So 4 is just simply saying, just put it all together into one cohesive unit. Call the function again recursively on smaller inputs if that's appropriate, or return the base case values when the inputs get small enough. My version. Oh, this ought to be interesting. Okay, let's see. Find the self-similar structure by taking something away and recognizing a smaller version of the same problem. Step 2, assuming the smaller version of the same problem is already solved, or just assume it's already solved. Step 3, take the solved smaller version and combine it with what was taken out initially to form a complete solution. Step 4, I guess I just took out I took step 2 and turned it into 2 and 3. And I considered the previous step 4 to be obvious. Okay. It's the same thing. So we saw this last time. I don't think this is that helpful to recall again. Let's just look at some examples, okay? So, I guess my examples are based off this idea. The idea is you start with n things, a problem on n things. Don't think of it literally like a sequence. Don't think of it like a numerical sequence anymore. This F means a problem with n things. Like Tower of Hanoi had n disks. F is the Tower of Hanoi puzzle. N is the number of disks. And what did we do? We solved it by saying if we could solve the Tower of Hanoi with one smaller disk, then we can combine those solutions accordingly. Okay? So the idea here is figure out how to separate it out into a smaller version of the problem combined with the stuff we took out to get the smaller version. And then after you iterate, you need to have this base case which says something like when there are, say, one disk, when there's one disk in the Tower of Hanoi, the solution is not recursive. It's just, you just move it. Okay? All right, so let's see some more examples. So step 1, consider various ways for simplifying inputs. In other words, try to conceptualize what's f of n and what's f of n minus 1. Okay? Try to figure out the smaller structure. For example, with string reverse, we started with all of the letters in the word, and in order to get the recursive solution, we took out a letter, and we called the same function on the smaller set of characters. Okay? With permutations of the word, we took out a single index from the word, and then we found all of the permutations missing that index, and forget about recombining it. We just, to find all the permutations of the larger word, we take an index out one at a time, and we find the permutations of the smaller set. That's a smaller version of the problem. For the Fibonacci sequence, you just need to know what are the numerical values of f of n minus 1 and f of n minus 2. Similarly with factorial, you just need to know n factorial, you need to know how, if you knew what n minus 1 factorial was, then computing n factorial is simple. Okay. So let's go in reverse of the examples. Okay? So step 2 is combine solutions with simpler inputs to a solution of the original problem. Or in other words, assume you have already solved the simpler problem. How would you use that to then get at exactly the larger solution? Okay? The larger problem solution. So let's go in reverse. If you knew what the value of n minus 1 factorial was, you would simply multiply by n times that to get the exact answer you're looking for. If you knew the values of f of n minus 1 and f of n minus 2, you would simply add them together in the usual arithmetic fashion. If you had all of the permutations missing, say, the ith letter, you would left append that ith letter to each of the smaller permutations, and that's how you would recombine it. You would do this for each letter as well. And then for the string reverse, if you had the solution to the reverse of these letters, you would right append the letter R that you took out initially. Okay? So again, you assume the smaller version of the problem is solved. You assume the smaller version of the problem is solved. You assume you know the smaller values input, and you just map out exactly how you would recombine them to get the larger solution. Step 3 is find solutions to the simplest inputs. In other words, 1 factorial is 1 or 0 factorial is 1. For Fibonacci sequence, f of 0 is 0, f of 1 is 1. Okay? That's going to stop the chain reaction. For permutations, all permutations of no letters is just the vector consisting of the single string with no characters in it. Or permutations with a single letter, that is the vector consisting of a single string object with the letter A in it. Okay? With string reverse, again, same thing. String reverse, the empty string should return the empty string, or string reverse on a single character should return a string object with that exact same character. Finally, step 4, implement the solution by combining the simple cases and the reduction step. Okay? So for factorial, we need the function set up so that factorial of n is going to be equal to n times factorial of n minus 1. But we need to check to say if n is equal to 1, don't call this again, just return a 1. Or if n is equal to 0, return a 1. Similarly with Fibonacci. Fibonacci of n is the sum of Fibonacci of n minus 1 and Fibonacci of n minus 2, as long as n is larger than, that's a typo, n is larger than 2. Let me just change that right now. Okay. Okay. Similarly, with, let's do the permutations, we took out each index, found all of the permutations on the smaller set of characters, combined it in, but then when that smaller set of characters was empty, or just a single character, we returned basically a vector consisting of a single string, which was no characters in it. Okay. And then for string reverse, it's the exact same thing, which is you just, and this is literally the code you would write. You write add to the reverse of those letters, and you check to see first if the input word has size, which is 0 or 1, you just return what was input. So here's an example which specifically outlines the different cases. So let's see. Check for base case, else recurse. Okay, so if word.size is bigger than 1, so if you have a word consisting of at least 2 characters or more, then apply the recursion step, which is take the substring consisting of exactly 1 character starting at index 0, append it to the reversal of the string with starting the smaller strings consisting of all of the characters starting at index 1 to the end. So that's a strictly smaller string. So you're going to keep calling reverse string over and over again until you get to the condition, which is word.size is equal to 1, in which case you'll just return the word. So this will return the word. It'll write append here. And then it will return that larger word. That'll exit out of its function call, combined with the character you took out there, et cetera, et cetera, et cetera. Okay. Fibonacci is similar. Fibonacci, numerical sequences are actually really easy. That's your homework gives you like 4 or 5 numerical sequences. I mean, you just take the formula and you can almost literally write it verbatim. There's really not much more to it. Okay? The hard part, what makes the assignment challenging, is just putting in the infrastructure for writing to a file and just setting up the recursive functions and the base cases. And once you've got that all figured out, there's really not any math you need to understand or know. It's literally just formula here. I copy more or less the exact same way it's worded math-wise into C++, and it all just magically works. Okay? So same thing here. If n is 0 or 1, return n, right? So f of 0 is 0, f of 1 is 1, so you just return the input. If it's negative, just return 0. Just pick some value for it. Yes, you do need to consider these cases. Yes, these are the most important cases to consider, especially in an interview. If you ever go for a coding interview, they're looking to know that you've covered all possible cases. They also want to know that you've covered what happens when n is, say, int max. Did you handle that case correctly? When does this function resort to numerical overflow? Okay? So you can write a function like this just fine, and in like 5 minutes, or not 5 minutes. You write a function like this right away. Okay? But then if you're not aware of all the possible things that could go wrong, the debugging aspect of this function could take you days, weeks, months, etc. Okay? So you have to have a keen awareness of for which values of n could be input and what are the possible values of n for which things could go wrong. I don't emphasize it as much when I teach because I figure this is something that you can do. These are detail-oriented things, and I'm just trying to give you all the big picture tools initially. Okay? But it's definitely something that you should be aware of, and if you want to dive deeper in that, you can ask in office hours, and we can go through some of the more tedious aspects of programming, especially numerically. But otherwise, you're just literally copying the formula, and instead of f, you're writing Fibonacci, and that's it. Okay? It's exactly as if you were just doing math, okay, or just writing a mathematical formula. Factorial is the same. If n is less than or equal to 1, return 1. Here, I'm really not doing a good job, okay? Because if n is negative, actually this should return some type of error. I think it's either a domain error or range error, to be more technical, but it really should cause an error if n is strictly negative. Okay? But then otherwise, you just call the function on a smaller input, multiply by n. That's literally the value that you want. Okay, but now let me just put the brakes on for a moment. Okay. This is one of the things that when I was a PhD student, my advisor really emphasized with me, and he gave me this lesson over and over again, which was we started thinking along a certain path. We did a bunch of little things. We worked out some various aspects of a problem, and then at some point, invariably, you come to a conclusion, and you say, oh, cool, that's an interesting conclusion. But you have to stop when that moment happens and just think and ask yourself, does this conclusion make sense with all the other body of knowledge that I've accumulated up to this point in time? Okay? So here's where it applies here. Don't just use a new tool because it's new or savvy or someone told you that you should always do it this way. Okay? You probably would not want to use recursion to calculate the factorial function. Okay? It's actually much more efficient to do it in the form of a loop. Okay? Same thing with Fibonacci. Okay? For Fibonacci, the recursive solution is actually the absolute worst thing you could possibly try and do. Okay? Yes, we will actually come up with a convincing argument which demonstrates why you would never implement Fibonacci in the recursive fashion. That's coming up in the next section. Okay? So just because you have this new tool does not mean you always have to use it. Okay? Sometimes it's a fantastic use of resources, sometimes it's actually not. So here's an example with Fibonacci. If you call Fibonacci on the number 7, really all you need are 7 values, right? You start with f of 0, f of 1, you get f of 2, you just save that, you get f of 3. All you really need to do is to save those current 2, add in the next one, and just kind of piggyback, or I guess leapfrog is the term, right? Until you get up to 7. But if you do the recursive version, f of 7 calls f of 6 and f of 5. What does f of 6 call? 5 and 4. What does f of 5 call? 4 and 3. Okay, so rather than just calling or calculating, say, 7 arithmetic operations, we've really exploded with the number of function calls and arithmetic. We're really you all know what I'm trying to say, okay? We're unnecessarily reduplicating calculations which have been done before, okay? So this is why at some point you stop and you think and you say, okay, what am I actually doing here, and is this the best thing for me to be doing? Okay? So the solution is always to think, okay? Don't just compute, but so on the other hand, this is what the non-recursive Fibonacci might look like. Would you rather read this code or the recursive code? Probably the recursive code, right? The recursive code is much simpler to follow and understand. This code right here, I mean, I wouldn't want to look at this. If something goes wrong here, it would take me quite a bit of time to actually work through all the details of, okay, what's assigning what to what and when and how should that be fold or fold 2? Which one of those goes there? Okay, so there's a trade-off. Sometimes, most of the time, the recursive solution is the most elegant and simple to implement, to read and to understand. But in cases like this is actually much, much more efficient than the recursive solution. Okay? So those are the choices you have to weigh. You have to weigh, for example, all right, I know the recursive version is bad, but is it really that much worse than having to look at and decipher code like this? Okay? The answer is actually, yeah, you would much rather look at code than this than work with Fibonacci recursively. But you won't know that until later. Okay, so also in the same idea as recursion is this idea of a helper function. So for example, when you actually implement, so consider the following function called isPalindrome. Do you guys know what a palindrome is? A palindrome is a word that is spelled the same forwards as it is backwards. Okay, so you call reverse string on this word, and you couldn't have told that it was, you couldn't tell if it was reversed or not. Okay, it's spelled exactly the same front and back. If you get rid of all those punctuations, a man, a plan, a canal, Panama is in fact a palindrome. It's kind of cool. So the question is how would you test to see if a string is a palindrome? How would you test to see if a string is a palindrome? Someone give me a very simple but possibly inefficient solution. Yeah. Okay, that was the simple, inefficient answer I was looking for, which is take the word, call reverse string on it, check to see if they're the same word. Okay? So again, we found a solution. Now what if and then the reason why he actually hinted at a better solution, but the reason why I wanted to start with this solution was so that we could think about this and say, wait a minute, what if the word is 1 billion characters long and the first characters and last characters are not equal to each other? Then it doesn't make any sense to do the remaining operations of reversing the entire string and comparing it. Okay? So we found a solution that just doesn't scale very well. Okay? Now, the simpler thing to do, of course, is to... Yeah, so you look at the first and the last one, like you said initially, okay? And you compare those. And now if those don't match, what do you know? Not a palindrome. You can just stop right now. Return false. If these do match, then what do you need to do? Move to the next two. Or, rather than thinking in terms of pointers, what if you deleted the first character, deleted the last character, and then did what? Call the function again on the smaller word. Okay. Light bulb. All right. Now, it's probably more efficient to just move the pointers one by one. Okay? Calling a function actually does involve some overhead. But the idea is still solid. The idea is actually not a bad idea. Okay? So, in this case, you may want to create a function called isPalindrome, and rather than actually calling it again and again and creating a new word, what you might want to do instead is take a hybrid of those two approaches. So you still want to pass in the exact same word. You don't want to make a copy of this word, but you also want to pass in the values of the current indices. Okay? So what you do is you say, okay, well, check to see if this word is a palindrome by checking if this word with these two indices match. And if those letters match, corresponding to those two indices, then increment the one on the left, decrement the one on the right, and call the same function again until they either meet or crisscross. So you don't want to just call the isPalindrome function with a bunch of starting indices and ending indices. You just want a single is palindrome function, you input a string, and it does the stuff for you. So what you're going to create is what's called a helper function. In other words, it's going to be a function that it gets called inside of the larger function. So you have the isPalindrome function. It accepts a constring reference. And rather than have the isPalindrome function be, the 3-parameter version, you just create the 3-parameter version. And, all isPalindrome does is start the chain by calling the function with the starting index and the last index. And then this function isPalindrome, the 3-parameter version of it, actually does the work of checking if the two characters match, and then calling itself, not the general isPalindrome function, but it calls itself again. Oh, do I not? I guess I have code posted on. Do I have it here? It may be. No, it's in the next one. We look at code 10. Let's do the most recent one. Oh, maybe that's too slick. Okay. There's my isPalindrome function right here. Okay. So there's both versions of it. The implementation is down here. There it is right here. So it checks if the indices crisscrossed. And if they did, it returns true, because if it got this far and the indices crisscrossed, everything checked out up until that point. Otherwise, it checks the two characters at those specified indices, and if they match, then it calls the function again by incrementing the two. The leftmost one goes incremented up, the rightmost one gets incremented down. Otherwise, it just returns false. Okay? So this isPalindrome function with 3 parameters is called the helper function. Okay. The final thing about recursion that I'll say, we're not going to really use this, I don't think, at all, but it's the same idea, but it might come up at some point where you say, wait a minute, I've got 3 different functions, for example, and f of n, well, at each stage it does call a different problem with smaller parameters, but it's this other function. And g of n maybe does something similar as well, but it definitely calls something with a smaller function. And you have everything basically going in a downward direction. Okay? Then it's fine. It works out. Okay? As long as all the paths eventually end in a base case, you're fine. Okay? So the mutual part is the sense that you're not strictly doing f of n and f of n minus 1. You're doing f of n and g of n minus 1, but g of n calls something either of the same level of a different function or of a smaller of a same one. Okay, so all the paths eventually lead to smaller inputs for which you can apply the base case. Okay, so, but the idea is very simple. We've been using size t. I guess when I first taught the course and threw this in there, there's a really nice article that I read at first, and it summarizes what I've been saying from the beginning of the quarter. So there's just a link to that article there. Okay, so let's take, well, for example, let's take the Fibonacci sequence, right? Okay, so how would we love to be able to write code? Write to file, say Fibonacci sequence. Do I want the sequence or just a number? Just do the Fibonacci number. Well, I'll just say Fibonacci, okay? Something like this. And then we can do Fibonacci of, say, 10. Oh, again, I can't do endl. I have to do /n. I run the code. I go to my files. Here's Fibonacci. Oh, oops. Let's call it .txt. Run it. Fibonacci.txt. That's f of 10. Fibonacci of 10. Okay? So that's how easy your homework assignment should be. All right? If you can get it to work out right. You have various recursive functions you need to implement for the next week's assignment, and it should be as simple as creating a write-to-file object, and then just in a for loop, as you would normally print out a sequence to the console, you can just print it to a file. So let's say do that. Let's say for I equals, say 0, int I equals 0, I less than, let's say 20, I plus plus. Call Fibonacci of I. We'll load up the file. And there are all the Fibonacci numbers. Okay. The other thing is these numbers grow quite rapidly, as do a lot of the sequences in your homework. So you can't really go beyond. Let's just see what happens if we try to do like 50. Well, first of all, it's going to take a lot longer than we thought, because I'm using the recursive version. Oh, this actually is going to take a lot longer than I thought. Okay, we're going to borrow the what is this? This is f? Okay, we're going to borrow the function f from the code. Okay, here's f. This is going to be the non-recursive version of Fibonacci. And you'll see that there is a very noticeable difference between the recursive and non-recursive versions. So here, for small values of the input parameters, the recursive one and the non-recursive one are going to be about the same. But as you saw, for n equals 50, the Fibonacci, the recursive one, actually took a noticeable amount of time, whereas right now, okay, we ignore the output, but it was like that. Now if we go to the file, oh, why does it go away each time? Okay. Okay, so there's a bunch of, okay. Now all of a sudden they turned negative. Is there any reason why they should turn negative? Yeah, it's not because somehow magically adding two positive numbers gives you a negative number. It's because you've exceeded the amount of space in the size of an int. Okay, so this number, whatever comes after 18363111903, that number is larger than int max, or in other words, the largest possible int variable that can be stored. Okay, so you got to get on the lookout for things like this. You can implement the functions, you can run the code, but again, these are the little errors that come in, and that these are nothing. No compiler complained. There was no runtime error. All that required, all that we have to go off of is thinking, as if to say, okay, this is what was supposed to happen. This is what did happen. Does this make sense of what was supposed to happen? And if it didn't, if this thing showed up, you have to ask yourself why. And if you don't know why, you got to find out. Okay? But the idea for the homework assignment is look, if you don't implement these classes which handle the file reading and writing for you, it's going to be a lot more difficult. If you do use them, it's effortless. Okay? And that's the main lesson that I'm trying to instill for 10B. Which is in 10A, you just try and learn how the things fit together and how they work and how, what is an if statement, what is a for loop. In 10B, we're converging towards this idea of not just how do you do it, but how do you do it in the right way, not the right way, but how do you do it in a way that makes the coding process much easier and high level so you don't have to do a lot more sort of deeper level thinking. Okay? So that's that, and when we come back on Friday, I guess we'll move on to the sorting and searching part of the course. Good afternoon. Today we are going to look into sorting, how you would sort a collection of objects. But first, before we do that, I want to go back and revisit the Fibonacci example because it serves to illustrate how when there are many different ways of solving a problem, sometimes the straightforward solution is actually the best one. Sometimes it's not. Okay? And sometimes the really neat, new, clever solution is actually not very efficient. And so what this is leading up to is the idea, as with sorting and searching and introducing how you solve problems via algorithms, the answer is, well, or the question that usually comes up is, how do you convince someone that your way of doing things is inherently better or worse than another way of doing things? So you can do time trial experiments, you can run an app or something, or a program or an algorithm a bunch of times and measure the amount of time and do a time trial, or you can do a little bit more refined analysis and say, okay, using a more quantitative measure of efficiency, I can prove that this algorithm is inherently a faster algorithm than this other one, in an abstract sense. Of course, when you implement all these things, there are a lot of other more complicated issues at work, but it's nice to know that, for example, in theory, this algorithm should perform inherently better than in all of its competitors. Okay? So let's first start out looking at the code. And I took this code from Lecture 10, Spring 2014. Okay? So I came up with, or I guess I coded up 3 different Fibonacci functions. So what I did was I took the usual Fibonacci, and I compared the recursive one versus the non-recursive one. So here's the recursive one, and I'm just kind of putting it in a counter here. See? So every time every time I call the function recursively, I'm adding +2 sort of function calls. Okay? So what we're going to get a chance to see, which is kind of the gobbledygook that spit out at the end of last lecture, we get to see exactly how inefficient this can actually be. And in fact, let's rather than just printing out +2, let's actually print out the values. So we're going to do like f of n minus 1, and then f of n minus 2. And that way we're going to actually get a chance to see sort of precisely which values or what numbers get called. So when n is, let's start out with n is 7. That was the example from the lecture slides. Let's see what happens. So we get a bunch of f's printing out. Let me actually put in a return carriage at the end there so it's easier to see. Okay, here we go. So, oops, do it again. Okay, so there's a list of all of the function calls to f, and you can see there's a lot. Okay, so we call f a lot. We're just looking at f of 7. In practice, if you were going to compute f of 7, you would just start with f of 0, f of 1, then do f of 2, then f of 3. You'd only need 7 calls total. But the recursive version forgets that it's already computed these other values. Okay, so if we up that 7 to say 20. Okay, now we've got there's a lot of stuff going on there. Okay, total operations was 10945. Okay, this is as opposed to, so let's look at f of n, just capital F of n. So this is the non-recursive version. And here I'm just calling +1, +1, +3 whenever I do arithmetic of some type. Okay, so here the +1 is I'm assigning 1 to fold. I'm assigning 0 to fold 2. Those are 2 variables. Here I'm doing basically the equivalent of, say, 3 arithmetic operations. So I'm keeping track of that. And again, if you just, I'm calling it on the same number n. And so we have Fibonacci of 20 done in two different ways. The recursive method, total number of operations or function calls was basically 10,945, whereas for the, and that's number of function calls. That's not even, that's pretty much the, sort of like the arithmetic. That's the number of arithmetic operations. But there's a lot more baggage associated with calling a function. Okay, so this is really bad. Whereas the iterative version really just did 6765 or 6,000. No, that doesn't seem right. No, that's the value of f of 20, 6,765. The total number of operations there, all those plus 3s, that can't be more than 100, right? Okay, so peanuts compared to the almost 11,000 operations the recursive Fibonacci looked into. Now there's this other version of Fibonacci which you should all maybe take a quick look at when you get a chance. It should be posted on CCLE. And it's F-slick is what I've called it. And what does it do? Let's see. OK, so it does pretty much the same thing. It runs in about the same amount of time as the, it's just an iterative version, but why did I call it slick? I called it slick because here, trying to debug this set of code is actually not very easy. If something goes wrong here, you'll have to sit down for at least 5 or 10 minutes and really work out precisely what's getting assigned where. There is a function called rotate in the standard set of algorithms in the standard library. And basically what I did was I created an array consisting of the elements 1, 1, and 0. So my sequence is going to build on itself. So it starts with, in reverse order, it starts with 0, 1, and then the next one, right? So I just gave it a value. And then what I did was I rotated the values so that the 1 and the 0 got pushed to the front, the 1 went behind, and then it updated that value to a 2, and then it kind of rotates it around. So it kind of takes this idea of, this is the current largest value. What you want to do is rotate these around and move the smallest value here, and then replace it with the sum of these two other values. Okay? This is even less readable, but it is a little more, it represents another way to solve the problem using built-in functionality, this idea of rotating. And this idea of rotating is actually a little bit more general than that, but you can take blocks of values and you can basically rotate entire chunks of values around. Okay? So just to show you that there are many different ways to solve a problem, this is probably slower than the regular F. It'll be definitely faster than Fibonacci, the recursive, but it's still, nothing really beats this bare bones, just take these variables, assign them, add, and just loop through it. That's about as fast as it gets. Sometimes using pointers can get you to go faster, but let's not worry about that. OK. So we have several competing algorithms, and we want ways to think about how to compare their cost and how to prove that one is maybe better than another. This brings us now to this very fundamental idea of sorting a collection of objects. OK, so this is a fundamental topic in computer science, and we're just going to briefly touch on two prominent algorithms, two very simple algorithms, and understanding how they operate at an abstract level, and then how to use them in solving problems. Okay? So how would you sort the following list of numbers from smallest to largest? This is where I open it up to the class, and I say, how would you actually do this? Any ideas? Say that again? OK, there's a method of the bubble sort. OK, can you describe it off the top of your head?
You just compare the two numbers, and then you put the largest one in the front, and then you just keep doing that, and then again, you just sort.
OK, so what he's described is what's called the bubble sort, but the name is not as important as the idea. What is the idea? The idea is you go through this list, and you take the 11 and the 9, and you only look at adjacent numbers. Okay? So between the 11 and the 9 is smaller, so in the eventual sorted list, the 9 is going to have to come before the 11, so you just swap locally the 9 and the 11. Then you compare the 11 and the 17. 11 is smaller than the 17, you do nothing. You go to the 17 and the 5. You swap those because the 5 is smaller. The 17 and the 12, you swap the 12 so that the 17 is in the last bit. Okay? Now, you've managed to completely sort the 17 or get the 17 in its right place. So you just repeat this process over and over and over again until nothing gets swapped. And if nothing gets swapped, then you know everything's in its proper order. Okay, okay, how about another way?
Start at the first number and look for a number that's smaller anywhere else. And then if it is smaller, switch the 2, and then move to the next number.
Exactly. So what he's just described is the selection sort, which is you start at index, say, 0, and then you try to find the smallest element among the entire numbers in the list. You find the 5, you swap it into place. You move to the next index, you then try to find the next smallest number, you swap it into place, and you continue on and on until you've swapped everything into place. Also good. Any other ideas? How about a bad idea? Somebody give me a bad idea. That it works, but it's going to be really slow. How about, okay, yeah.
You could just randomly scramble the list, and each time you scrambled it, then check if they're in order.
Exactly. You randomly scramble the indices, and then you check if it's in the right order. And if it's not, you do it again. You could list all permutations of the numbers, and then find the one that's in all order. Okay, so there's different levels to designing an algorithm, and this sort of was when I was doing my PhD thesis, I did it on randomized algorithms. And the beauty of these randomized algorithms in particular, and just in general, is there's the different levels of, all right, initially I have this set of tools and I can apply them directly and I can solve the problem, but it's not done yet. Okay, I solve the problem, but it's not very efficient. So then I think harder, and then I solve I'm like, oh, okay, I squeak out more efficiency, more provably than what I had before. Yay, I can write a paper. Okay, so you've accomplished something. And then the further depth you're willing to go, the greater efficiency you can unlock. Okay, and this is a wonderful type of field and a subject because it gives you initially very encouraging results, as if to say, all right, here's something I can use right away. It works. Can I make it better? Okay, so with that idea in mind, let's explore initially what's called selection sort. Okay, so start with the 11 and test the numbers 9, 17, 5, 12 for the smallest, which is 5, and then swap the 11 and the 5. Okay, so that was the idea that was said earlier. Okay, swap the 5 and the 11 into place, but then you repeat this. So you start with the list on top, you swap the 5 and the 11. The 9's already in place, but you still have to search every single element to make sure that you knew that. And then the 11 gets swapped into place, and then the 12 gets swapped into place, and then the 17 ends up at the end. Okay? This actually has a name. It's called selection sort. Here's the pseudocode for it, which is point to index 0 with value 11, search through all values starting with index 0, and return the index of the minimum value, swap the values in those two positions, point to index 1, and repeat. Okay? Question? Hang on, let me go back so I can. So, say again. Are you saying you want to do like a rotate thing with 3 elements instead of just swapping 2? Yeah, you can do that. And again, that's a great idea. That's great. That's exactly how you want to be thinking. That's the direction. Okay. We're going to show that that's not going to make that much of a difference, or you'll know why that's not going to make much of a difference when we dive even deeper and look at a different method. But that's definitely in the right direction, which is, okay, I have this idea, and it seems initially kind of slow, which is, I'm searching through all these elements. Certainly there's got to be a better way to do this than continually, searching through all these things. Okay, so you're on the right track. Yeah, but I can tell you in advance that's probably not going to make it noticeably more efficient. Marginally, yes, but we will unlock an even better version of this. Yeah, but that is definitely the right idea. Okay, so let's now continue down that road, which is think about the wastefulness of the algorithm or the cost associated with this algorithm. Okay, we have the right mindset, which is we want to make this as efficient as possible, but we want to start with at least a baseline of something that works and see and measure sort of how many operations it's going to take. So, okay, let's think about what we're doing here. Okay, first, to find the minimum of n numbers, that takes order of n. Okay, it takes about n operations. If I want to find the minimum of a list of 100 numbers, I pretty much have to look at every single one. So that's approximately 100 sort of operations is what we would sort of say. Okay, so 100 lookups. If it's a billion numbers, that's a billion lookups. Okay, so you get the idea of how we're trying to cost this. Once you find that smallest index, you swap with the current min. That's relatively cheap, right? If you know exactly where the elements are, you just swap the values. That's maybe costs 2, operations to do that. Okay. So in total, it's something like n plus 2 operations. You have to visit all n elements, plus you have to swap 2 into place. So that's sort of like an n plus 2. Okay. You could argue that it's like n plus 3 or n plus 10 or n plus 17. But we're going to show that it's not going to matter. Okay, n plus a fixed number of operations. Okay, so we might as well pick 2. But then we repeat this process, right? Once we swap it into place, we do the exact same thing, except now we're searching for the min over n minus 1 elements. Okay, so if we have 100 elements, the first time we sweep through 100 elements, we find the min, we swap it into place. Now we're looking at 99 elements. We search through each one, find the min, swap it into place, then 98, 97, et cetera, et cetera. Okay? We repeat this process until there's only one number, and that ends up being the max in the list, and that ends up being exactly where it needs to be. So this is how you would actually think about how the algorithm, how long the algorithm takes, or costing the algorithm. Okay? So like I said, initially, you have n plus 2. So just take a look at that upper right, upper left, n plus 2. You have to visit all n objects, and then the plus 2 is to swap it into place. The next step is the next term. N minus 1, that's why it's in blue. Okay, I've color-coded it, so it's easier to parse. N minus 1 remaining elements, plus the 2 to swap it into place. Plus n minus 2, plus the 2, dot, dot, dot. Okay, so you keep doing this. The dot, dot, dot means continue this trend until there's 2 elements left. At the end, you swap or you don't swap, depending on if they're right or not. Okay, but it still takes, say, 2. You have to look at each one. That's the blue 2. And then you have to swap or not swap. Just that decision itself can be seen as the green 2. Okay? So what we're really doing here is we're adding, and this is where the fun comes in. Okay? So I don't expect you to know any math. I don't expect you to know any math. I do expect you to know what arithmetic is and how to add and multiply things together. Okay? But I don't expect you to know any of these formulas that I'm using. I would always give you those on an exam. Okay? I would expect you to know how to formulate the cost, and then if you can write it in that form, then you can apply the formula. Okay? Very basic application of summations. Okay? But let's just go from that first line to the next line. Don't get too scared. I took all of the blue numbers. Two times n minus 1. So all my green 2's got collected at the end there. And all of my visits are in the dark blue. Okay? So I've got the sum of the numbers 2 plus 3 plus 4 plus by 2. And of course, I had to add 1 to make it the full sum, so I had to subtract 1. That's where that minus 1 comes from. And then the green 2's just come along for the ride. And then I just do the simplification. Okay? Now, if you're worried you're going to mess up the algebra, you're like, oh, I haven't done algebra in so many years, I'm going to mess up. I would have gotten 5, I would have gotten 17 or something. Don't worry. Also, because the constants themselves aren't going to matter either. What? Okay, so the way you cost algorithms is actually really nice. It's not incredibly detail-oriented. It's more big-picture-oriented. Okay, so what is important is that you have an n squared here. Okay, what is important is that all the other terms have an exponent that's less than the n squared. That's the essential part of this expression we're going to be very keenly aware of. Okay? So what this is saying is that if I want to sort a list of, say, 100 elements, the n squared means that 100 squared is the number of visits to each entry I'm going to have to times I'm going to have to visit. Okay? So if I take 1 billion elements, I'm going to visit 1 billion squared times, approximately. Okay? So the n squared tells you about when you scale up the penalty you pay, and that n squared is why it's very, very powerful. This is the leading term. All these other terms are going to be insignificant compared to what information this tells us. Okay? Let me explain what I mean by that more precisely. Okay? This is the punchline. We're going to take a polynomial, for example, like this, or a math expression like this, and we're going to convert it to what's called big O notation. Okay? So what is big O notation? Big O basically says, take this expression and extract really just the core property that I'm interested in at a high level. Okay? So like I said, with this algorithm, you can cost it precisely using this formula on the left. But what we really care about is the fact that it's big O of n squared. In other words, the leading term is an n squared. We don't even care about the divided by 2. Okay? We just care about that leading term. Okay? So here's why. Here's why. Okay? So let's think about the simplest estimate for the left-hand side. All right? Now we're going to think of n as being really large. When n is small, none of these things really matter. Okay? You want to sort 100 elements versus 1,000 elements. It's still really fast because you're using a computer. Okay? It's still going to be really fast. But if you want to sort 1 million or 1 billion objects, that's now where these things are much more important. So let's think about it. Okay? Let's when n is 1,000, for example, n squared over 2 is 500,000. And the remaining terms really just kind of add a little bit of extra stuff, right? But if someone were to ask you, oh, like if that was the cost of a house, for example. I'm just kidding. You can't buy a house in LA for that price. Okay, but let's say this was the price of a house or something, right? And someone says, how much did you pay for the house? And this was the number. You wouldn't say, oh, I paid exactly $502,500. You'd say, I paid about $500,000. That's what the big O is trying to capture initially. Okay, it's the sort of the order of magnitude. Is it $500,000 or is it $5 million house? Those are two different orders of magnitudes. Okay, the $5 million is more realistic, right? All right, bad joke. Okay. So the 500,000's kind of the ballpark figure, but that divided by 2 is still sort of part of the idea. Okay? So let's see why we're going to get rid of the divided by 2. So let's forget about the coefficient 1/2 on the n squared, because rather than thinking of like bottom line number of operations, really what we want to think about is how do we scale up? Okay? So if I can sort an object of length 100 in 5 seconds, how long is it going to take me to sort a list of length 200? Okay? So the constant in front will give you that baseline reading, but when you're not really interested per se in exactly how much time it's going to take for 500 elements to be sorted, you want to compare that to, say, I sorted 100 elements in 5 seconds. If I double that number, the time should do what approximately? Should it double? Should it triple? Should it quadruple? Should it go up by a factor of 10? You want to get an idea of how the time of the algorithm changes when you, for example, double this input size. Okay? So when you do that, what you have is you have this quotient equation set up. In other words, you have, if I want to go from n equals 1,000 to 2,000, then the amount of work goes up by a factor of a certain amount. And the amount that it goes up by is a factor of 4. So if to sort a list of size 1,000 takes some amount of time, to sort twice as many number takes that time times 4, okay, or quadruple the amount. That's the idea we want to capture. Okay? I know it takes, say, X amount of time to sort 1,000 numbers. For twice as many, it's 4x. Not 2x, but actually 4 times the original amount. Okay? That's why the constant goes away. Okay? So to bring it all together, we take away the smaller term, so the 5n over 2 minus 3, and we take away the coefficient of 1/2. And really what we're left with is an n squared algorithm, a big O of n squared algorithm, which means if you double the input size, you effectively quadruple the amount of time that it takes for the algorithm to run. Okay? That's the idea. So for example, suppose to sort a list of 10,000 numbers takes 1 second. Then to sort a list of 20,000 numbers would take about 4 seconds, because we're quadrupling the amount of time it would take. And to sort 40,000 numbers, we're doubling this, say from here to here, or we're quadrupling this. And if we're quadrupling it by a factor of 4 again, and that gives us 16 seconds. Okay? So several different ways to think about that one. But this is not good, right? I mean, if we're double the input size and it takes 4 times as long, that doesn't scale very well. That's not a very desirable property to have. Okay? Because now imagine you have a database with millions or billions of entries. How long would it take to sort? Okay? So maybe plug in 100,000 or 160,000. Okay, here is a formal definition which you don't need to know for this course, but which may help you if you're the type that likes to see things very formally written out. Okay? The idea behind big O is that when n gets large enough, the quotient of the two expressions stays bounded. It doesn't go off to infinity. It doesn't decay to 0. Well, it could decay to 0. That's fine. But it doesn't go off to infinity. So for example, if we looked at this expression here, if you took calculus, okay, if you've taken calculus, you don't have to have taken calculus, but if you've taken calculus, you can think of this like if you take the quotient and you take the limit, it goes to a finite number. And the limit is finite, not infinity. Okay? Then you can use the big O. That's another way to think about it. Really, you're just dropping off the lower terms. For example, here, we can drop off the 3. And we can get rid of all the constants. So we have an n squared and we have an n. That's fine. This is big O of n squared plus n. That's a perfectly legitimate way to write this. It's technically correct. Another technically correct way is the simpler just big O of n squared. Because if I were to divide n squared by n squared plus n, eventually I would get closer and closer to the value of 1. And I would stay bounded. Okay? So that's the idea. This is formally how you can think about it, but you don't have to think about it this way. Okay? So again, there's a lot of just information on this slide. Let me just try and parse it for you. First bullet point. Operations like plus, minus, times, division, these are actually really well implemented. These are really fast. Okay? So, but they all take maybe roughly the same. Actually, you know, dividing and taking square roots, for example, those are actually really slow compared to just adding, subtracting, and multiplying. Okay? Division is notoriously slow, but you won't even notice it. You won't even notice the difference. So let's just assume they're all the same. Okay? Anytime you actually access an element in memory, that actually takes time. Okay? If you do it too much, if you put it in a loop and you're accessing millions or billions of elements, you will notice the slowdown. Okay? So we think of that as a cost of size 1. Okay? To access an element, say costs 1. To multiply, costs 1. To divide, costs 1. To add, costs 1. Just makes it simple across the board. Okay? Simple to think about, simple to reason about. Okay? You can think of it as consisting of a bunch of smaller steps, but just assign them all the same unit 1. Okay? Remember, constants don't matter. So just give it a value of 1 and forget about it. That's the beauty of this big O notation. You don't have to be meticulously thinking about the details. Okay? So again, technically the n squared over 2 plus 5n over 2 minus 3 is a lie. It is a flat-out lie because it does take a different amount of time to test whether or not two elements are equal. It takes time to access each individual element. It takes time to actually do the swap. But we're just assuming all of those take the same amount of time because we're not interested in that full expression. We're just interested in this big O. And regardless of how all those little steps actually cost, it's still going to have the same big O answer. That's the beauty of it. Your ignorance is bliss in this case because it can change over time. It might be implemented on this computer differently than this one. But this big O of n squared still stands no matter what machine you're on. Okay? As long as it's a perfectly reasonable machine that doesn't do anything wacky. Okay. Basically, the takeaway is that it's not practical to be incredibly precise on how the computer actually does things. Okay? You can't know how it actually does things. Different computers optimize code in different ways. Different compilers optimize code in different ways. But they all share the same thing in common, which is that you can't beat certain paradigms. In other words, if an algorithm's order of n squared, it's going to stay order of n squared. Okay? That's the theory aspect of it. The amount of time it takes to perform those operations might get faster as time goes on, but that idea of doubling the size quadruples the number of operations, that idea is still there, and it will continue to be there. So here's some examples that you may want to go over with your TAs, for example, if you're not as familiar with how to do this big O stuff. Ask your TAs to draw you pictures and go over these things if you're confused. Let's just go over the first couple just because they're a little more interesting, and then I'll leave the rest as an exercise. Okay, so the top one, n squared plus 2n plus 1. You pick out, if it's a polynomial, you just pick out the leading term and you drop the coefficient, and that's your big O. It's as simple as that. N plus 1 to the fourth, it's very simple, right? When you FOIL that out or expand that out, you don't even need to think beyond just the leading term. The leading term is n to the fourth. You forget about anything else after that. Okay? N squared plus 3 to the power of 6. Again, that n squared, that leading term of that expansion, is the n squared getting raised to the 6th power. And that's n to the 12th. Okay? When you have an n squared raised to another power, remember the exponents multiply. N to the 100 plus n to the 99. Again, You might think, well, for small n, that really, small values of n, like 5 or 6, that makes a huge difference. But eventually, the n to the power 100 wins out. The other thing is now 2 to the n plus n. Anything where you've got a constant base that's larger than 1 raised to a power of n, that's going to trump any polynomial. That's going to grow exceptionally fast. Okay? Doesn't matter what the base is, as long as the base is strictly larger than 1, 1.0001 to the n is going to eventually beat out any polynomial. Okay? I'll summarize those rules on the next slide. If you have 2 to the n plus 3 to the n, same form, the larger base wins out. Okay? N plus log of n, log is an incredibly slowing function. This is the logarithm function. Oh, did I specify the base? What's that? Am I saying base 10 by default? In this case, it doesn't matter because the n versus the log n, the n's going to always outgrow it. But typically, I have to specify the base, or at least tell you what the default value is. By default, it's usually 10. Here's the beauty. You don't actually need to know the base. And you know I'm all about that base. All right, good. That one got a laugh. All right, okay. But I'm not all about that base, because the base, that base, doesn't matter. And we'll see why in a minute. Okay? That base, no trouble. Okay. All right. Note, all logarithms are related by a constant. Okay, so this is the change of base formula from high school or some other similar form. You don't really even need to know the exact form of the log base changing out. I don't care if you know that. Okay, what I do care about is, all right, if I want to take a log in this base and convert it to a log in another base, I multiply by a constant. But what does big O do to constants? Just throws them away. Okay? So essentially, all logarithms behave the same in this big O analysis. This is a wonderfully beautiful thing because now I don't have to worry about what base do I mean, what base is the default. Is it base 2 because we're in computers and it's binary? Is it base E because that is the natural base? Or is it base 10 because, well, if you're going to actually work in the decimal system, you're probably thinking about base 10. Okay? So you get to drop the base. Okay? So let's see. In general, log grows slower than any polynomial. Log raised to any power, typically, as long as it's just a polynomial, like log to the power of 5, grows slower than any polynomial. Also, here's a little trick. You guys remember, you guys have to, this is one thing you are going to have to remember. Okay? If I have log of n to the power of something, I can take that exponent and I can move it in front to multiply. That is one thing I'm going to expect you guys to know. Okay? So ask the TA to go over examples if you're not as familiar with it. Taking log and log again, that grows extremely slow. That's even, plug in n equals 10 to the 81st. That's about how many atoms there are in the universe. It's tiny. Okay? So even log of 10 to the 81st is what, like a couple hundred? So logarithm is an exceptionally slow growing function. Okay? If you have things like log of n squared plus log of n, just think of log of n like n, and the one with the larger power wins out. Okay? So I've listed a bunch of rules, and then just keep this kind of picture in the back of your mind, which is log of anything, even raised to a power of b up here, is less than n raised to any positive power, and that's less than really anything larger than 1 instead of the 2, could be a 3, etc., raised to the power of n. Okay? Look at the practice exams, though, because there are several problems there that some of them are actually quite tricky. Okay? So look those over before the next midterm and make sure you have a complete understanding of the growth of the various functions. A note on me. Nobody cares. All right, let's see. Just to give you an idea, this is not just well, I guess my thesis work was academic mostly. This is useful, okay? For my thesis, I actually did devise an algorithm to do something better than any other algorithms, but how did I prove that it was better than any other algorithm? I did the costing, okay? It was a little more technical than what I've showed you here, but the core idea is exactly the same, which is, okay, previous algorithms to do the same thing required big O of n to the 5 quarters. The first part of my thesis, I got an algorithm that did it in n to the 3 quarters. Improvement, okay? 3 quarters is less than 5 quarters. That's a good thing. And then finally, we got it down to n to the 1/2. Provably better than the alternatives, okay? It's not machine independent. It doesn't matter how those things are actually implemented. The idea is, regardless of the implementation, I was able to demonstrate that, yes, my thesis problem or algorithm was in fact better than any other competing algorithm that was out there. Okay? That's a powerful type of statement. Okay? So you're only going to be able to use this idea to say very basic things, but just I wanted to make sure that we all are aware of that there is a very intense sort of background underlying this development. Okay? And it is extremely useful. Okay, so now that we've gotten this selection sort out of the way, we've seen how to cost it. Okay? Let's do better. What do I mean by better? What I mean is selection sort was big O of n squared. Let's try to beat it. Okay? Here's a possible candidate. So selection sort is big O of n squared. Now, consider this algorithm. You have a collection of numbers. You split them into 2 halves, sort each half, and then merge them together. Okay. So think about that. I have a list of elements here and a list here. Initially, they're not in sorted order. So they're scrambled up here, they're scrambled up here. I sort them individually, and then I merge them together. Here's the idea. Okay? Here's the merge part. So wait a minute. I split it into half. I sort this, and now I merge them. Okay, let's do the merge. Okay, so how does the merge work? So the merge works by, I point to the 5, I point to the 1. 1 is less than 5, I put the 1 into my put the 1 in place. Then I point to the 5, I point to the 8. Well, the 5 is lower than the 8, so I put the 5 in next. Then I point to the 9, I point to the 8, the 8's the next smallest, and I continue down this line. Okay? So the merge is itself accessing each element at least once. Okay? So you can't really do better than, if you have n numbers here, you have to access each one of them at least once. So at best, this is big O of n, right? This is how you should be thinking. If I have to access every single element, I can't do better than n, because I have to access at least one. Maybe I access them 5 times each or 20 times each, but it doesn't matter. As long as that number is fixed, like 20 times at most, or at most 5 times, then it's big O of n. Okay? Well, but let's think about this for a moment. Ignore this line right here. Just ignore it. What are we doing with this merge sort? We're trying to lower the big O in the sorting algorithm. But what is the select? Wait, did I say selection or merge? Sorry, merge sort. Sorry, yeah. Go back to merge sort. With merge sort, that was my fault for possibly being confusing. What we want to do is split the data into 2 halves, sort those smaller collections of elements, and then piece them together. Which means that this is Okay, now you can look right there.
Recursion.
Yeah, recursion. Okay? In order to solve the sorting problem on exactly n elements, we assume we can solve the problem on n divided by 2 elements. That's certainly smaller than n. Then we piece them together. Okay? So this is the idea. F of n is the amount of time to sort exactly n objects. To sort the first half then costs f of n over 2. To sort the second half costs f of n over 2. What is f of n or f of n over 2? Well, we'll get there. We'll get there. But just this idea of sorting n elements is f of n. We've managed to split the problem into taking something out and then solving a smaller problem. How do the pieces fit back together? They fit back together by taking each of the smaller halves and then merging them back together. We saw how to do that. That is a recursive solution. Okay? But this is harder to cost, right? So bit costing the selection, or cost, I don't know why it says bit, but just costing the selection sort was non-recursive. Okay? So in other words, the number of steps to take after you put in the fourth number into place, that was just an explicit number. But to sort n elements, you need to know how the cost to sort half as many elements. So the costing itself is recursive. And this is where a lot of the principles of combinatorics comes in. You don't need to know any of them for this class, but this is the idea. The idea is you have this structure, and you have within that structure a substructure that looks like the larger structure. Okay, this kind of self-similar type of behavior. Yeah?
So you're still using selection sorting on the half, right?
No. Great question. You're still using selection sort on the halves. The answer is no, because what you're doing is, how do you sort an element of size, a list of size 1? You don't, right? How do you sort an element of size 2, a list of size 2? You break it up into 2 each. You sort each of those. That's done, and then you merge them together. How would you sort an element of size 4? You take the 4, you split off the 2, you split off those 2, you merge them together. There is no selection sort. There's only splitting and merging. Okay? So that's the key idea. With recursion, right, it magically, you assume you can sort the smaller lists. And if you can sort the smaller lists, the merge is what is the explicit part of the algorithm. The merge is what is not recursive. But it's the ability to say, to solve the problem on sorting n objects is the same as sorting the problem with half as many objects. That's where your recursion comes in. Okay? That's the power. And there's no other technique you need other than to just merge them back together. Okay? So I think, is this the last slide? No. Okay. Like I said, we'll start with this next time, but just to summarize, like I said, with merge sort, you have to access each element at least once. So you can't do better than big O of n. And it turns out that big O of n, yeah, it's maybe like 5 times n is the total number of times, okay? But merge part is big O of n, and so what's going to end up happening is we're going to be solving this equation right here, okay? So we have, say, T of n equals the task to sort n objects is equal to the task of sorting half as many objects twice plus merging those elements all together. Okay? So we'll pick up with this next time.